Hi everyone. So this is the part 3 of the slide. Okay, so this is the where that we are looking at the operating system approaches, okay, to support mutual exclusion. There are semaphore, monitor, and message passing. Okay, let's look at semaphore. Semaphore is one of the method in OS approach. So what is semaphore? Semaphore is a variable that has integer value. Okay, so it's giving a signal, so a process can stop at a specified place when it receives a signal. So semaphore can be initialized, okay, to a non-negative integer value from the beginning, right? The same weight operation decrement the semaphore value. Okay, if the value become negative, process that executing this same weight signal, same weight function will be blocked. Okay, and the third one is same signal. Okay, if same signal operation, it's increment the semaphore value. If the value become not positive, so the process is being unblocked. So we will look at this using an animation provided from the Stallings book, okay, and hope that you're able to understand the scenario of having this semaphore in order to achieve mutual exclusion. Okay, let's start with this animation. So this is a demonstration of mutual exclusion achieved through the use of semaphores. So for the beginning, the value of mutex or the semaphore is set to 1. Okay, and then we have the mutex list, which shows the process that will wait to use the critical section. Alright, so we have 3 processes, process A, process B, and process C, that will running according to their turn. Okay, so let's begin. Okay, so process A now begin to execute. So it will start to execute the first line, and then now it's begin to execute the wait mutex, okay, which is similar with same wait. So now the first line in the function is to decrement the value of mutex. So now the value from 1 is become 0. And then check if value smaller than 0. Is the value smaller than 0? No. So it will basically continue to they will exit and then continue to the original or the main function, and then continue to execute to critical section. Okay, so comparison is made to determine if a process is already in its critical section. So if none, if the value is false, okay, then the process exit and then go to the main function. Then process A is allowed to enter its critical section. Right? Then, while in the critical section, context switch by CPU scheduler. So now this is process B turn. So process B begins to execute, and then execute the wait mutex. Okay, the same thing. So go through value, decrement the value of mutex, and then we get -1. So test, okay, value smaller than 0, yes, then we put it in the mutex list. Okay, so process B added to mutex list, and the process B now next is to block the process. Because process B cannot be in the critical section because A is still in the critical section. Okay, so context switch. Then next is process C. So process C the same, wait mutex, and then decrement the value, right? Then value smaller than 0, yes, so bring it into the list. Okay, and then block process C. So what happened now? Get back to process A. So process A resume the execution in the critical section, and then when finished, it will execute the signal mutex, which is the same signal, value +1. So meaning now the value become -1. If value smaller or equals 0, okay, remove process from list. Is it smaller or equal? Yes. So remove one process. So that's mean process B. Okay. So because this comparison to determine if any processes are waiting in the mutex list. Okay. So remove process B from the list, and the process is no longer blocked. And then now process A is doing the remainder lines of the code. Okay, so once the context switch, process B will continue to run in critical section, and then exit. Okay, execute the signal mutex, and then increment the value of mutex value, compare the value to see if there is process in mutex list. If yes, then remove the process and wake up the process. Okay, and then the process B can do the remainder. Then context switch, process C resume and enter the critical section. Okay, when finished, same thing, go to the signal mutex, increase the value of mutex, and then okay, the test of value is failed. So because there is no process waiting in the mutex list, so exit, and process C can do the remainder of the code. So by using semaphore, we can ensure that only one process can be in the critical section at one time. Okay, so that is why semaphore is quite popular to be used in the operating system in order to control the execution of the process. The implementation of semaphore can be implemented, okay, if we use like atomic primitive to same weight and same signal. So atomic primitive means that the operation of the function must be execute and until finish. Okay, then we can continue to, if you want, if the OS would like to context switch with other process. Okay, same thing with the same signal. So there is no interruption in between. And it can be implemented also in hardware or firmware. Okay, so because it's OS level, so normally we can do it in firmware level. Okay, software schemes such as Decker's or Peterson algorithm can also be used together with semaphore. So semaphore can be implemented also in the Decker's and Peterson algorithm. Right, so there are basically some option, okay, for implementing the semaphore, right? And also we're giving you also the problem that can be integrated, okay, that can be solved using semaphore. So that one I think you can go through as long as you get the concept what is semaphore. Okay, so you can imagine you have a guard that basically looking after you while you are in the critical section. So while you are in the toilet, for example, in our daily life, so the guard will basically tell you that the critical section is occupied, so you need to wait, right? So we are assuming that the door of the toilet is not locked. So if locked, then this is kind of guard. Okay, so we're waiting, then the user comes out, and then we can go in. So that's the what can I relate the use of semaphore. Okay, it's actually to lock the critical section so no one can interrupt while process running in the critical section.